Yeah, I'm ready. So hello and welcome to my talk. First, let me thank the organizers for giving me the opportunity to be part of this wonderful workshop. I already learned quite a lot about the superconducting diode effect just today and also yesterday. So I'm really excited to be part of this. I also know that it's already pretty late for at least some of you in the audience. So I hope that my talk is going to be as instructive and as entertaining as possible. So as we already heard, this talk is about actually the companion theory work with reference given down here on the experiment down here that we just heard about on the superconducting diode effect at zero external magnetic field in a twisted graphene system consisting of 3 layers. Before starting, let me acknowledge my collaborators. So on the theory side, let me acknowledge help from Harley Scammell, and the experiments, as we have already heard, have been performed in Jiali's group, where Jiang Xiazi Lin has been particularly important, who gave the previous talk, and Jean Ziribibun, among other experimentalists. Now, today I'm actually in the rather unique situation of being the only theorist to give a talk about a graphene moire system at a conference. And although we already had a few introductions to this field, I thought I will also start with a brief one focusing on a few maybe slightly different complementary aspects that will be particularly important for understanding the remainder of the talk. Now, let me start with the, well, by far most well-studied and most well-known example of a graphene moire system, which is twisted bilayer graphene, where, as we've already heard, we start with 2 layers of graphene, we twist them against each other, and then you put one on top of the other, which creates this spatial interference, or if you will, moire pattern of carbon atoms. And now for certain discrete commensurate angles, or at least approximately for small angles, you will have translational symmetry on the Moire scale. And once that's the case, you can Fourier transform and start talking about the band structure. Now, to understand the band structure, let's first know that if you rotate something in real space, it also rotates in momentum space. Let's indicate here in red, say the Bronson of the red graphene layer, and in blue, the one of the blue layer. And if you work out the details, you can convince yourself that the Moire Bronson is related to those two in this way. Now, if we first start in the limit of decoupled layers, just to understand the band structure, we can immediately conclude that there will be 2 Dirac cones coming from valley plus of the individual graphene layers. Now, things are periodic in momentum space. And so I can draw several copies of the Moire Bronson, and for a commensurate angle, they will line up as shown here. And so we will have 2 additional Dirac cones associated with valley minus. Now here we are interested in data of the order of 1 degree, where we'll have a couple of thousand small hexagons in the big hexagon. So the momentum transfer from plus to minus on the Moire scale is extremely big, and hence to a very good approximation, there's no hybridization between the 2 valleys. And as a matter of fact, throughout this talk, I will assume that the non-interacting band structure has valley as a good quantum number in these systems. So to compare with single layer graphene, we have double the degrees of freedom. So on top of the 2 spin flavor degrees of freedom and the 2 bands, which give these Dirac cones, we also have 2 values. Now, if you really want to understand the band structure, you got to introduce some tunneling and compute it. So the tunneling here is shown here on the left. Is modulated on the Moire scale. So G are the reciprocal lattice vectors of the Moire lattice of smallest magnitude. And this calligraphic T are 2 by 2 matrices in sublattice space. So there's a W0, the intra, and a W1, the inter-sublattice tunneling. And these parameters will be used later on in the talk. This is why I introduced them. Now, you can compute the band structure by coupling these Dirac cones. And here, as a result of such a calculation, you're shown for a single spin and valley flavor. First of all, we see that there's still Dirac cones despite the tunneling. And the reason for that is that there's a symmetry, C to Z, a 2-fold rotational symmetry times time reversal theta that protects these Dirac cones. Now let's take a look at the evolution of the band structure once we decrease the twist angle. As you see that the Moire Bronson becomes smaller and also the bands become increasingly flat. That's maybe not that surprising, but something kind of unexpected or remarkable, or if you will, magical happens at 1.1 degrees, where the bands are almost perfectly flat and then start dispersing more. Now, you would expect that in the vicinity of the magic angle, correlations are enhanced, and that's exactly what you find. But it was still a big surprise when in 2018, it was for the first time shown experimentally that this leads to both superconductivity and a variety of other correlated phenomena, such as the spontaneous emergence of insulating behavior, which we now refer to as correlated insulators. Now, this is all I'm going to say about twisted bilayer graphene. So it's basically only one example of putting different, layers together and building something new of, as I call here, playing quantum Lego. There are various other ways. You can put, for instance, together 3 layers, maybe with an alternating twist angle configuration. You can start with bilayers and twist them against each other, or you can use a chiral twist angle configuration. Furthermore, there are other van der Waals materials that you can use, maybe to induce spin-orbit coupling in an already existing graphene moire system, or you can use them to build something entirely new. Now, in this talk, I will talk for the remainder now about trilayer graphene with and without spin-orbit coupling. So more specifically, in the first part, I will review some particular recent theory work where we discuss instabilities in trilayer graphene, and also talk a little bit about some earlier works that are relevant in this context, which just gives us like an introduction to the system, set up some nomenclature, some instabilities, and it will eventually form the basis of the discussion, the second part, which is about the zero field superconducting back effect. Okay, so let's get started with mirror symmetric twisted trilayer graphene. The system consists of, well, 3 layers. The outer 2 are parallel and the middle one is twisted against the other 2. If you look at the structure, you immediately see, as also the name suggests, that there's a mirror symmetry. And once you have such a symmetry, all bands, including those that are shown here in this one-dimensional cut, decay into mirror even and mirror odd bands. And it turns out that the mirror even sector, modular rescaling of parameters, is exactly equivalent to that of twisted bilayer graphene. And this is, for instance, the reason why you see these almost flat bands here in red. Furthermore, the mirror odd sector is equivalent to single layer graphene, which is the reason of having these highly dispersive Dirac cones in the band structure. Now, in experiment and in theory, you can now break this symmetry by applying an electric field or displacement field, and this will lead to a hybridization between these different sectors. But as you can see here, the Dirac cones will actually still survive, and that's because C to Z times theta is still a symmetry. Now, this system has been realized experimentally now by a variety of groups. Let me maybe mention here the first, to the best of my knowledge, 2 experiments that reported physics in this system. And they were transport measurements, and they already found a very interesting set of complex many-body physics. Let me here maybe just flash a few key results. So this is a schematic phase diagram that I took from Pablo's paper. So one axis here is displacement field. The other axis is electron filling, and so filling fraction. And there are several lines. So there are reddish lines, which correspond either to a gap or a Dirac cone. And there is orange lines, which I refer to as reset behavior, which means that if you go from here through here, spontaneously the number of active degrees of freedom in the band structure is reduced. And I will later on provide a possible microscopic explanation of where this comes from. Furthermore, in blue, there are superconducting regions, some of which actually show quite interesting behavior, some of which are can survive actually very large in-plane magnetic fields, much larger than at least naive estimates of the Pauli limit. And this seems to indicate that there's something very interesting going on about superconductivity in the system. Now, since it's going to be important for the discussion of the diode effect, let me in this first part really review only the essence of this recent theory work, where we would discuss, theoretically, the correlated normal state behavior in the system, the insulators, semi-metals, and also this reset behavior. And then based on that, make statements about the superconducting order parameter for, in our opinion, very natural description of its mechanism. Okay. So to get started, and in the spirit of a canonical theory talk, I'd like to first specify the Hamiltonian I'm interested in. So there is H0, which just captures the non-interacting band structure. For our analytics, it's just the flat bands plus dispersive Dirac cones. For the numerics, we also take into account various remote bands. The interaction is taken to be a gate screen Coulomb interaction, where rho of Q is just the density operator. So F dag and alpha, the electronic creation and annihilation operators in this low energy degrees of freedom that are kept. And F are matrices in the same space, which capture the form factors, basically just the matrix elements of the Bloch functions of the band structure. Now, for now, let's neglect spin-orbit coupling. And so the form factors will be diagonal in spin space. And since we also, I said before, Valley is a good quantum number of the band structure, so they will also be diagonal in Valley space. And if you work out the details, we'll see that this leads to an enhanced spin symmetry, which I denote by SU2 plus cross SU2 minus. It's simply the independent spin rotation in the two valleys. Now to get started with the correlated behavior, let's start really in the simplest limit. I'm not sure how simple it really is, but it's at least the simplest, in my opinion, non-trivial limit of correlated physics here, which is defined as follows. Let's start with making these bands perfectly flat in the TBG sector. We assume that there's no displacement field quite yet. And we also go for the experts to the chiral limit, which means that we set the tunneling matrix elements between same sublattices, this W0 that I mentioned earlier, to 0. Now the Hamiltonian has this form. So there's the sum of the interacting Hamiltonian of graphene, the interacting Hamiltonian of twisted bilayer graphene, and a density-density interaction between those two systems. The first thing we could show is that the ground states of this Hamiltonian at integer filling of the TBG sector are also exact eigenstates of the full Hamiltonian. And furthermore, if you adiabatically turn on this density-density interaction, they're guaranteed to remain ground states in at least a finite range of this adiabaticity parameter. I can't prove whether this includes lambda equals 1, right? That's not possible. But at the very least, it tells us that the ground states of this Hamiltonian are an extremely good starting point of our analysis. And luckily, we have a good understanding of them because graphene is a correlated yet symmetry unbroken semi-metal. And twisted bilayer graphene has been studied in a lot of details. And in particular, recently, there has been a lot of amazing progress in theory. I just mentioned a few papers here. And in particular, in this specific limit, it is understood that there is an entire manifold, SU4 plus SU4, of degenerated ground states of this Hamiltonian. So the idea now is to take these insights and start from this fine-tuned limit and then turn on parameters such that we eventually reach the realistic system that is realized in an experiment in the lab, and just to study the physics. Now, before we resort to any sort of approximate energetics, we can just use exact group theory techniques to develop candidate orders out of this high symmetry point. Basically, you look at some submanifolds of this manifold that correspond to states that transform under the different irreducible representations of the symmetry group of the actual system that you're interested in. And this leads to this set of candidate orders. So don't worry, maybe some of you are not so familiar with these systems. I don't expect you to understand or even read all of these orders. I just want to give you a flavor of how rich the physics can be in the system. And on the next slide, maybe just mention a few of those states. So they're again listed here in this table. It's the same 11 states. Let's go through some of them. For instance, there's spin polarized state. That's the simplest thing you can think of. Literally just means that you favor one spin flavor over the other. But there's already an interesting subtlety to point out, meaning that this state is exactly equivalent to what we call here spin valley polarized or spin valley locked. And that simply comes from this SU2 cross SU2 symmetry. Remember, so if you have something that's ferromagnetic in the two valleys, you can independently rotate the spin. So you can also rotate it into this state. Now we call these pairs of states Hund's partners simply because there is a Hund's interaction between the two valleys in the actual system that couples the spins in these two valleys. And depending on the sign of these J Hunds, you will either realize one or the other. Now, there are further states. There's a valley polarized state, which simply means that you favor one valley over the other. There are various more complicated states. There's so-called inter-valley coherent IBC states, which simply means that you spontaneously break the valley charge conservation symmetry, or put differently, the fact that valley is a good quantum number is spontaneously broken due to interactions. And there are various, quantum Hall, quantum valley Hall, and related states, as well as the Hund's partners. Now, what we did in this work, and I don't really want to discuss too much details, just set the basis for the diode effect. We did analytical perturbation theory and numerics to compare the energetics. And on this next slide, I use a very schematic phase diagram to summarize the 4 ASCII results. So here, this is displacement field as a function of electronic concentration in the system. The charge neutrality point, for instance, at small electric field, we find an intervalley coherent state, which is for the experts distinct from the TBG, from the state, the IBC in twisted bilayer graphene, because it's still a semi-metal protected by a symmetry. And for larger displacement field, you reach an insulator. Now, the energetics in the vicinity of nu equals 2 is very similar, with the sole difference that we, on top of this, get spin polarization. So as you can see here, spontaneously, one spin flavor is pushed entirely below the Fermi level. So you reduce the number of active degrees of freedom by a factor of 2. And this is our interpretation of this reset behavior. So schematically, the phase diagram here looks like this. So there's spin polarization in some region and possibly some additional instabilities corresponding to the correlated semi-metal and insulator in the vicinity of mu plus 2. Now, of course, this is a conference on the superconducting diode effect. So I better start talking about superconductivity, which is the next topic, obviously. But before really adding superconductivity in this phase diagram, let me maybe go one step back and talk about a previous work that Reinze Matstein, a paper that Reinze Matstein I wrote, where because it's important to understand the pairing in the vicinity of this high symmetry point in a system which has these two valid degrees of freedom. So we basically asked the following question: how many different phase diagrams are there in these different graphene moire systems, both with C2Z and without C2Z symmetry, of this form, where one axis is temperature and the other is a parameter like denoted by delta here. You can think of it as the Hund's coupling that breaks this SU2 versus SU2 symmetry. And the answers in general are quite complex, depending on which channel of superconductivity you're looking at. But it turns out in the trivial representation, which I focus on here, it's rather simple. There are only two options. One is a unitary, one phase diagram is associated with a unitary triplet, and the other with the non-unitary triplet. But the question we ask, which is not yet answered on the slide, is what happens with these lines, right? Are there secondary transitions by extending these lines to the left and right? And the answer is entirely determined by symmetry. Turns out the triplet state has a Hund's partner, to use that language, that is a pure singlet, whereas the non-unitary triplet has a singlet and triplet at mixed phase as its Hund's partner. And I think just to point it out, I think this is quite remarkable that something like this is possible, because it deviates from the conventional mechanism of singlet triplet at mixture, which is based on spin-orbit coupling, hence a reduced symmetry. And here it happens already. I mean, this is without spin-orbit coupling at this point, and it's due to the proximity to an enhanced symmetry. Something like this happens. Now let me come back finally with this information to the phase diagram and talk about pairing. For this, we have to specify a model. So what we use here, we assume, well, electron-phonon coupling is relevant, and it's really crucial to get the TC right. It's consistent with several screening experiments. And we assume that it's predominantly in this SU2 cross SU2 symmetric channel. And there are additional fluctuations, additional corrections here from nearby particle Hall orders that tip the balance towards either side of these phase diagrams that I showed earlier. So let's discuss this concretely. Maybe let's set the Hund's interaction, the Hund's coupling to be negative, which is what you get if you project the Coulomb interaction. And so let's study superconductivity, maybe starting with the superconducting region 1 here. And here fluctuations from this nearby order are relevant. In this case, you find that it's a triplet superconductor. In this superconducting region over here, you get a non-unitary triplet. And for the opposite sign of J Hund's, and admittedly, we don't really quite know what the sign is. For the opposite sign, so let's just study both, right? For the opposite sign, we here get a singlet triplet mixed state. And this superconductor will be either a singlet or singlet and triplet at mixed state, depending on microscopic details. Now, just to connect to previous experiments, so actually both of these options, no matter what J Hund's is, are consistent with this Pauli limit violation in the superconducting region 2. And let me also point out that maybe some of you might be saying, well, this guy is talking about triplet, but triplet is going to be destroyed anyway by a little bit of disorder. This is slightly different here, actually, because of these two values, as we showed in this paper. There's actually some kind of Anderson theorem, if you will, for triplet here, which means that triplet is actually protected against impurities that are smooth on the atomic scale, but vary on the moire scale, non-magnetic impurities. Okay, so this is all I wanted to say about constructing the phase diagram of Trilayer. And if you take a look at it, and of course we should remember that we are here at the conference on the superconducting diode effect. After all, you might be wondering, well, wait a minute, if this is really true, what I'm being told here, that superconductivity coexists with this order, isn't spin polarization already like applying a Zeeman field, and shouldn't we get a diode effect here already at zero field? The answer is actually no. And the reason for that is there's still symmetries that make sure that the critical current is the same in one direction and the opposite direction. So we don't expect actually a diode effect at zero field here. And as far as I know, at least none has been reported or is visible in the data of previous experiments on trilayer graphene. However, if you think about finding some way, maybe spin-orbit coupling, of translating this broken time reversal symmetry in the spin channel to the orbital channel. For instance, you add spin-orbit coupling, like Ising spin-orbit coupling, which couples the spin literally S here to the Valley degree of freedom, which generates a little bit of Valley imbalance, for instance. Then you've actually broken all symmetries that you require, that you need for a diode effect, but at zero magnetic field. And this was the motivation to very carefully look for the diode effect in trilayer graphene, tunnel coupled to tungsten diselenide, in this case here, which induces spin-orbit coupling. As we've already heard in the previous talk, a superconducting diode effect-like behavior was indeed found. I know that the previous talk already described this in quite some detail. Just for those of you who only for some reason only happened to attend this talk, or to remind some of you, and for those of you who just watched this recording, let me just very briefly summarize. So here you can see the VDI curves as a function of applied current, and you can see clearly that it's the critical current. This line here is highly asymmetric with respect to zero, and this is a zero magnetic field. Now, this is based now in our interpretation on spontaneously breaking time reversal symmetry, so it should be trainable by a magnetic field, and it actually is. It turns out that a perpendicular magnetic field can train it rather easily, whereas an in-plane magnetic field cannot. And this will be an important constraint on the theory later on. And in these systems, you can tune the electronic filling just by applying gate voltage. And so you can see here at another filling, the effect can be more prominent. And something I find quite remarkable is you can actually, if you go from electron to hole filling, you can actually reverse the orientation of the diode. And in the remainder of the talk, I would like to provide possibly theoretical microscopic explanations of these rather striking phenomenology. To this end, let me start maybe with really the simplest picture possible. Let's forget about spin-orbit coupling again, just for a second, and just imagine that by whatever mechanism, we have generated some Valley imbalance, okay, in the system, and let's study the behavior of superconductivity as a function of this Valley imbalance, which we assume is present. Let's maybe write down some equations for the modeling. We model a non-interacting band structure described by this E of K and eta, where eta just refers to the two valleys, plus and minus. That also takes into account the Valley imbalance. So here, this is without Valley imbalance. So the two Fermi surfaces in the two valleys are just mirror images of one another. But eventually, we will turn on some Valley imbalance. Then we assume that there's some attractive interaction in the Cooper channel, which we now decouple. So you get something like this, where delta is the superconducting order parameter. Again, we keep both singlet and triplet component at the same time. Here, actually, our focus on SU2 plus SU2 symmetric interactions. It's the reason why there's this simple trace in this space, but later on I will generalize that. Now, given such a theory, it's straightforward. Oh yeah, and maybe I should mention that we focus here on inter-valley pairing, meaning that we have Cooper pairs of electrons in valley minus and plus. And the reason for that is simply that, that at zero in valley imbalance, you have Karamas degeneracy between the two valleys. So you expect inter-valley pairing to be energetically favorable, and we expect this to hold also in a finite range of valley imbalance. Now, in such a theory, you can compute the free energy, and there's this prefactor of the quadratic term, which depends on momentum through the particle-particle bubble, and its momentum dependence is plotted here on the left. So without valley imbalance, not too much of a surprise, the maximal is the cube 0, we get a 0 momentum Cooper pairs. That's of course as expected. Let me just mention that you have to add, of course, in such a description, higher order terms. In this SU2 cross SU2 symmetric limit, they look like this. I mean, the details are not relevant, just maybe to connect it to something I said earlier, the sign of B2 determines which of these two phase diagrams is realized. But most importantly, we want to get to the diode effect. So let's try to compute the current, which we do similar to many other theory works. You can think about it as applying a phase gradient, which shifts the superconductor to a finite Q. And then you just compute the current as a function of Q, which gives you the allowed currents a superconductor can carry, and hence gives you a critical current, which for this situation is plotted here on the left. And as you can see, it's symmetric. There's no diode effect. And of course, there's none. We have time reversal symmetry of C to Z symmetry. We shouldn't get a diode effect here. Before coming to the diode effect, let me mention that I said earlier that superconductivity might on top of this coexist with spin polarization of some form. The results I'm going to show next are qualitatively also valid there. You just have to modify this theory to an effective spinless theory. Okay, so finally, we approach the diode effect. So let's assume that there is some value imbalance. And let's compute the particle-particle bubble. And what you first find is that there's still the maximum at q plus 0. And actually, the reason for that is that we have threefold rotational symmetry, which forces gamma to have this form, such that in a finite range of value imbalance below some critical value, this maximum is pinned to q plus 0. But there's a diode effect because you break all symmetries that are required for it, as you can see in this plot here. Of course, if we apply more value imbalance, at some point, the maxima will move to finite q, and you get finite momentum pairing along with the diode effect. Now, of course, if you exaggerate the strength of the value imbalance in the real system, at some point, superconductivity will disappear. But as a theorist, we can make it very strong and let it survive very large value imbalance, such that eventually reach an intra-valley pairing state, which also has a diode effect. But I suspect that this state has a very high momentum and will be extremely fragile. But for convenience, it's added to this slide. Okay, so this is the simplest scenario possible. And now let's go back to this plethora of instabilities that I mentioned earlier, right? So out of this U4, this U4 limit, there are a lot of states that emerge out of it. I listed here again. It's actually categorized into U1 valley symmetric, so states that don't affect the fact that valley is a quantum number, and states that are inter-valley coherent, so that spontaneously couple the two values. And the question I would like to ask is, if we assume that any of these states coexist with superconductivity, which of them can give rise to a diode effect? And here we have to be careful, because if we have spin-orbit coupling, this will also affect these instabilities themselves. So just to mention this explicitly in this context here, there are four commonly used types of spin-orbit coupling: Ising spin-orbit coupling, the Rajba spin-orbit coupling, Kane-Meillet, as well as the sublattice imbalance term. And here in this expression, S is spin, eta is valley, and rho is sublattice. And here P1 simply indicates that this spin-orbit coupling is only present in the first layer to a significant degree, because that's the one that's proximity coupled to this layer here. Now, there are first principle calculations that indicate that this Kane-Meillet and sublattice imbalance terms are much smaller than the other two, so we will focus on this first two, which indeed are estimated to be sizable. So they're of order of or comparable to the energetic separation that we find between some of those states in numerics. So they're not a small perturbation necessarily. So we can study now how these states evolve as a function of spin-orbit coupling. So spin-orbit coupling does two things, right? I mean, from a symmetry point of view, first of all, it reduces the symmetry. And this has two consequences. So for the instabilities, you will see that there are instabilities that have spin polarization perpendicular to the layer, parallel to the layer, depending on whether you have an easy axis or easy plane. So this enhances the number of candidate orders, but it also reduces them because it reduces symmetries, and hence states that are previously symmetry distinct can now start coupling. And this is, for instance, the case for valley polarized state, which will mix with a spin polarized state, which was based on the intuition I mentioned earlier. Now, you can do the same exercise for the IVC states, and you can again repeat the exercise if you also turn on Rajba spin-orbit coupling. You here get four different sets of candidate orders, and here actually nothing changes. Now, the important question is which of these states can give rise to a diode effect, and it turns out that these first two sets can, whereas this latter two cannot, and also none of these IVC states can. So we're left with these two different classes of states, 4 here and 2 here. And let's zoom in and discuss them in a little bit more detail in the following table. Okay. Oops. So here I have again the same 4 plus 2 states, and I indicate what the associated critical current asymmetry has to be proportional to. So in the valley polarized scenario, this is the only case where we don't need spin-orbit coupling, as I said earlier, and I demonstrated even in an explicit calculation. But in case of all the others, we do require spin-orbit coupling. But it is non-zero, so it actually does give rise to diode effect in all of those cases. Now, another important constraint is trainability. And remember, it's easily trainable by an out-of-plane field, but not by an in-plane field. You can work out the trainability for all of these orders. It's shown here, first for the Zeeman field, out-of-plane, in-plane, and beta here refers to the breaking of C2, C3Z symmetry, threefold rotational symmetry associated with either nematic order or strain. We expect it to be small. Basically, anything proportional to beta means it's not easily trainable. And as you can see, the first 4 states are actually consistent with the observed trainability, whereas the latter 2 are not. And this actually carries over to the situation where you also include the orbital coupling. So these first 4 states are more natural candidates, and this includes the valley polarized state or valley balanced state, to be precise, which actually mixes when spin-orbit coupling is present with all of these other 4 states. Just for future reference, maybe for future experiments, let me mention that there's another distinction between these 2 scenarios. Namely, the critical current has to be C3 symmetric in the case of these first 4, and it's not in the case of the latter 2. So maybe future experiments would be able to distinguish these scenarios or further nail down what is going on in the system. Okay, so that's that. Let me maybe just very briefly make a comment on the fact that we have the sign reversal that I mentioned earlier. So this is, of course, a very complicated question, but at least in the simplest limit where we assume that there's no spin-orbit coupling and valley polarizational imbalance, we can at least extract some information from it, from the sign reversal. Remember, the way we model the diode effect in these calculations is there's a renormalized dispersion due to the valley imbalance. And this dispersion involves the non-interacting band structure plus this valley polarization part. Bz is simply its strength, and G of k eta with this constraint due to time reversal symmetry is the basis function. Basically some matrix elements of the order parameter in the band basis. And the band structure is approximately, it's not quite true, but approximately symmetric around 0 energy, which is actually the case in this chiral limit again. And this means that if you go from electron to hole doping, you have to replace this effective dispersion in this way. So you set a minus sign here. And let's for now just assume that valley polarization, the form of it doesn't change from electron to hole doping. Then what you get is, if you look at this equation, you can relate it to the behavior in the electron dope case in this way. And if you use this in the expression for the particle-particle bubble, you get this relation between gamma and the particle-particle bubble at electron and hole filling. And since the current is related to the gradient of this function, you get that the critical current for a certain direction at electron filling is, in this simple model, equivalent to the current in hole filling, the particle-hole conjugate filling in the opposite direction. So in other words, you get a sign reversal of the asymmetry. Now, again, I'm not saying this explains why it behaves like this. I view this more as an approximate justification or interpretation of the fact that from here to here, it's naturally understood by the fact that the form of the valley polarization doesn't change tremendously if you go from electron to hole filling. All right, and just in the remaining minute or so, let me just briefly for completeness mention that there's in principle a more exotic possibility, namely there are more complicated states than those that I just discussed so far, superconducting states. So if you look at the irreducible representations in the case of a spin-orbit coupling, there are 2. One is one-dimensional, that doesn't break any symmetry. Another one is complex or 2-dimensional, and it involves a nematic state, but also a chiral state. And this chiral state actually does break time reversal symmetry. And at least in principle, you can use this to get also a diode effect, at least in principle. So you could imagine that there's some composite order, we see here, where C1 and C2 are just the expansion coefficients of the superconducting order parameter in its basis function. So for this state, they would be 1i, and then C is non-zero, and it describes broken time reversal symmetry. So if, and don't have any direct indication that this is the case, but if this composite order parameter condenses at some temperature T star above Tc, this breaks time reversal symmetry, and assume that superconductivity in the sense of quasi-long range order of some charged operator sets in at some temperature Tc below T star, and C stays fixed once you reach the critical current, you can at least in principle by symmetry have a diode effect. And it's also consistent with the trainability behavior But again, as I said, I personally believe because this is a very exotic scenario, it's also a very complex superconducting state, likely very fragile, that the previous interpretation is likely more natural. Okay, with this, I'm at the end. I think I should be right on time. So let me briefly summarize the discussion, the talk. So in the first talk, part of the talk, I discussed some recent theory work on Trilayer graphene, which gave us some understanding of what the candidate orders at the very least are, and was also motivation to look into the diode effect carefully in the first place. Then we discussed the diode effect at zero external magnetic field. And I provided some possible microscopic origins of that. So I mean, there's some time reverse symmetry breaking that is going on and that happens spontaneously. We discussed that superconductivity coexisting with 4 candidate orders that are all ultimately mixing with some form of Bally imbalance is a natural microscopic scenario. But of course, as I said, also a more exotic pyro superconducting scenario is in principle consistent. We discussed a little bit the very complex behavior of the sign reversal with the electric field. But of course, I should say, I mean, this is really just the first step. This is really the first theory work on trying to understanding this quite novel zero field diode effect of this very strong nature in an entirely, as we believe, homogeneous system without any Josephson junction and so on. And so, of course, there are a lot of open questions. And so I'm really looking forward to further theory works in this direction and also more experiments. And also, of course, looking forward to your questions. Thank you.
Yes, thank you, Professor, and for the next talk. And do we have questions? Yeah, Vala.
Hey, thanks for the nice talk. I was wondering if you had any, and I apologize if I missed something about this, but regarding this, zero field state that appears at only finite current, finite DC current. Do you have any thoughts about that? Because what's also funny about that is it also implies a time-dependent phase across the entire superconductor, and that's also somewhat weird in my view, because you have to have accumulated some voltage drop before reaching the zero voltage state, the zero resistance state. If I understand that this is a truly differential measurement.
Yeah, that's the question, really, right? What really happens in this state? I mean, first of all, I think this is absolutely surprising, and that's one of the big open questions. So I don't have a definitive answer to that, but if I may speculate, and there's actually, something I could imagine, and I'm currently, in fact, already working on, is this idea that you see. I think what is really unique about this system, is that everything, at least in this interpretation, seems to be happening, within a single homogeneous system, right? So it's not that we added a ferromagnet on top, or so it's literally the same electrons that do both, right? And so what that means is that they also, all of them, I mean, all of the orders that I described, they also feel the current that you apply to the system. And so something I think is possible, at least, it's allowed, I think, by at least on phenomenological ground, I've convinced myself that this is possible by symmetry. I don't really know whether the numbers add up, but something that you could imagine is there's a coupling between a current you apply for a given current direction and the value polarization itself. And the value polarization is actually, I mean, of course, the way we treat it theoretically, we assume that this is a huge energy scale, right? That is there, that is fixed. And on top of that, there's superconductivity. But in reality, maybe the energy scales are not that, I mean, maybe are comparable, at least somewhere in the phase diagram. So what I could imagine is that if you apply a current in one direction, you actually strengthen in value polarization and hence further suppress superconductivity. And if you do the other way, and at least by symmetry, these couplings are possible and it should happen, you can actually suppress it. And if the superconductor is very close to being suppressed by the value polarization that is present without current, this could at least in principle give rise to such an extreme behavior. And this, by the way, this behavior is something that you really see if you look at the density dependence. That's something you really see at the end, at the largest density where superconductivity is about to disappear. So it's very strongly affected by, let's say, Bally imbalance. So I think at least that's the picture I'm currently having in mind. I'm even working on. But I can't really tell you whether it's quantitatively, going to really give this, because at the end of the day, there's a lot of complex physics going on once you're in the vicinity of the critical current in a two-dimensional superconductor. So,
And okay, great. Thank you. And another follow-up, unrelated, kind of related question that you touched on. So you were describing at least a homogeneous system, and I think your theory applies to a homogeneous system. But we know that with these twist angle stacks, there's a lot of it. There can be a lot of, say, twist angle homogeneity and stuff like that. So I was wondering, you had this categorization of the different possible phases and which ones can have diode effects and which ones can't. But the go no go on the diode effects there, I assume, are for the homogeneous case. And I wonder if inhomogeneity can activate the diode effect in a couple of other situations. Because, for example, just like with this is maybe a very simple analogy, but in the case of the squid, with the loop inductance, if you bias it asymmetrically, then you will also get a diode effect. It's kind of an inhomogeneity. As long as you've broken inversion and time reversal, then you can, and in principle can get it. So I'm wondering if inhomogeneities can also develop a diode effect in a small sample like these typically are. In some of those other phases,
yeah. That's a good point, and I think generally speaking, in all of these systems, the sample homogeneity, this twist angle homogeneity, is of course a big question and is an issue. So I think generally speaking, maybe the part of these symmetry arguments I would be that I'm worried about is maybe the wrong word, but where we have to be careful is that this rotational symmetry. I think this is something that will be strongly affected by that, right? Remember that it's pinned to Q equals 0. This argument. This is something that would that's weakly broken by disorder. Twist angle disorder, for instance. Well, if you have a sufficiently large sample, I would think that things average out. And so I would think that the local C2Z symmetry pattern which you're emerging would probably average out, I could imagine, in a sufficiently large sample. But I mean, it's hard to rigorously exclude it. I would think that the effect is unlikely to be that strong, personally. I mean, it's an extremely strong effect. And so I think, in principle, as I said, yes, in a sufficiently small sample, that could play a role, but I would think it's not a supernatural explanation to really get this sizable effect. Also, given the fact that we have some indications that the spin polarized scenario in magic angle trilayer graphene that I described theoretically is maybe at least in some samples might be realized, and so with a little bit of spin orbit happening, I think it's just too natural to have a little bit of Valley imbalance. So this is a quite natural scenario. But you're absolutely right. I think twist angle and any form of inhomogeneity, but in particular twist angle homogeneity, is something that needs to be considered quite generally in this.
And maybe an even simpler form of inhomogeneity might be just the fact that you have edges, right? And those there you have sublattice symmetry is broken there usually, right? So
absolutely. No, I mean that will, of course. I mean, if you break all symmetries, then any of these orders, at least those that break time, some of them actually, some of them don't break time reverse symmetry modulo some, time reverse symmetry. And so some of them might be still excluded, but the C2Z part, I think
maybe it would be interesting to know what things, given if the edges could activate something, outside of the current categorization, perhaps that would suggest that a Corbino geometry could be useful. Ruling such things out.
Absolutely.
So it would be good to know what are the ones that false positives that could come from edges, so to speak. That would be interesting to know.
That's absolutely right. Yeah.
Okay, thank you. Sorry for all the questions.
Well, it was great. Thanks.
Yeah, I see another question in the chat from Mast, and the question is, how can we probe these predictions about which terms VP, SVP, and etc. are responsible for SDE and the training in experiment? Can we tune those inside too?
Yeah, so the question is, if I understood correctly, I can just read it. The basic question basically seems to be, if I go back maybe to this table, right? not here it is, this one, right? So these are the remaining candidate orders. And the question is, how can I further distinguish between all of them, right? If I understand correctly, let's see. So distinguish within them. Okay, so first of all, I think if you have really strong spin-orbit coupling, then at the end of the day, let's say these four, right? They all mix. So from a truly fundamental theoretical point of view, you can't distinguish between them when they're strong spin-orbit coupling, just because they're whenever you have one, the other will be induced, right? They're just the same symmetry channel, right? With strong spin-orbit coupling. These are not equivalent. So between these two, you can further distinguish. Well, I mean, the trainability already told us something, right? But also this rotational symmetry can distinguish between these two classes. Now, a more subtle question is, how can you distinguish between, let's say, within these four, okay? And in order to do that, what you really have to do, you have to get a lot of statistics, I would say, in different setups and samples, because what you would have to do is vary the strength of spin-orbit coupling, ideally. Okay, I'm not entirely sure what the best way to do that experimentally is. I mean, there are certain things that could come up that come to your mind, but maybe ideally you would vary spin-orbit coupling strength, because then you can actually distinguish between the two, because if it's not too strong, they don't fully mix. And you can also see, for instance, that in certain orders, I mean, the trainability would be affected and all of these kinds of effects. So this would be the way to distinguish between them, varying the strength of spin-orbit coupling. But other than that, if you're in the strong spin-orbit coupling limit, by definition, these four orders are the same. So.
Yeah, okay. So do we have any other questions? If not, let's thanks Professor Scheurer again for the nice talk. And then now,
thank you.
Yeah, and now we are in the discussion section now. So we are free to ask questions and have some discussions.
No, actually, if I can ask Matthias, because I just didn't have enough time to raise my hand.
Sure.
So
Okay.
the coupling for the Cooper pairs, as far as I understood, right, was inter-valley coupling.
Mm-hmm.
So could you please repeat what is the physical explanation for that? You quickly told, but I didn't fully get it.
Yeah. That was too fast. I mean, in principle, I could share my slides again, but what you see, the two valleys are those degrees of freedom that are related by time versus symmetry, right? I mean, if you that just follows from, if you just look at original graphene, right? K and K prime are related by time versus symmetry. And I mean, usually, I mean, generically, the reason why superconductivity is dominant in many materials at low temperatures is that we have this Kramer's degeneracy, time versus degeneracy, which makes superconductivity so strong, and because it's right at the end of the day, this is how you get the Kubo logarithm, and that enhances superconductivity. And so pairing that is between the valleys takes exactly advantage of this degeneracy of the two different valley degrees of freedom. If you had intra-valley pairing, okay, with time versus symmetry, that's of course still has a diverging susceptibility at some point, but it's going to be at a much lower temperature, simply because if you look at K and K prime, a momentum K and a momentum minus K in a given valley, they won't be both generically on the Fermi surface. And that's why this is subleading, right? But if you increase valley imbalance, right? Let's go to the extreme limit where you push one valley entirely away, but there's only one valley left with a Fermi surface. Well, you probably get intra-valley pairing. And also, by the way, I mean, just to say that about the stability of those spaces, right? If you have realized an intra-valley pairing state, that's a state that has a huge momentum, right? That has a momentum that is related to the original microscopic graphene scale. So there would be some kind of pairing state that is, spatially varying on the scale of the original graphene layer. And this is likely speaking extremely fragile against any form of disorder, I would think. And so this is why I said I suspect that this is not realized.
I mean, there are these FFLO states and I don't know.
No, they are, but you know, I tried. Yeah, that's right. I mean, I'm not saying I can exclude it rigorously, and graphene can be made very clean, right? So you know, maybe it is realizing some sample would be even more exciting. But what I basically said, what also the point I wanted to make is that this argument and the diode effect, this phenomenology does not require having this exotic state being stabilized, right?
Okay. Thank you.
Sure.
Do we still have some questions, even to your previous speaker? Oh, I see a question to Mathias, to you, in the chat, and the question from Benjamin, and this question is maybe a side question to you. What did you mean with smooth impurities on the atomic scale? Could you please give an example?
Yeah, a twist angle disorder. That's the answer to the question. That's an example, but maybe let's say a few more words, right? So the idea behind this Anderson theorem is that, you see, usually if you have a triplet state on a single Fermi surface, right, you because of, you know, just you have spin degree of freedom, so just by anti-symmetry, you require some momentum dependence in the orbital part, right? I mean, that's just that's what you require, and if you add impurities to that, then whenever you're scattering between 2 points on the Fermi surface where the phase of the order parameter is different, it's pair breaking. And now this is the reason why triplet is generically rather unstable. Now in this twisted systems, we have, it's related to the previous question actually, we again have these two valleys. And now you can have a state, that a triplet state that is basically constant in each valley and changes sign between the valleys. And now what you need in order to break, we have a pair breaking effect, you have to scatter between the two values. And that's a huge momentum transfer. Remember the picture at the beginning of my talk. That's a huge momentum transfer in momentum space of the order of the original graphene layer. So you need impurities that are sort of like sharp, that have enough, you know, that are localized strongly enough to transfer from one valley to the other. And if you're something that is super smooth, it just won't have a sufficient Fourier component on the microscopic scale. That's the reason for it. And twist angle disorder, which we believe to be at least a very crucial and important type of disorder in these systems, clearly falls in this category, at least generically.